All right, so today we're going to begin our discussion of contact with sort of a simplistic overview of contact mechanics from very basic principles where we'll spend a lot of our time talking about these very simple one-dimensional idealizations of contact constraints, how they appear in the format of solving mechanics problems, as you're previously already familiar, how they relate to basic mathematical principles of constrained optimization. And we'll then, if we have time, dive into some of the extensions of these same ideas into the domain of two-dimensional and three-dimensional finite element analyses, and how we can generalize similar descriptions of these constraints into that format of considering not just, let's say, a one-dimensional block, coming into contact with a rigid surface, but rather what happens if I have two elastic bodies coming into contact? How do I define similar descriptions of, contact constraints? Okay, so if you're really interested in this subject, and if it's something that maybe even pertains directly to your kind of like research, I would highly recommend this particular reference by Peter Riggers, Computational Contact Mechanics. It gives a really nice introduction to the subject, very comprehensive in terms of its presentation, and it covers all the things that you could possibly want to know and probably more on this particular topic. So I'll follow through and present some of, the similar organization of topics as Professor Riggers. But yeah, he's eminent in the field and probably one of the most notable contributors to this particular subject. In any case, yeah, so that's more for your own reference. I think you might even be able to find this text for free online, or at least you probably have university access to it through the library. All right, so let's talk about contact. Up to this point, we've really been dealing with simple situations where we can idealize some structure as having some elastic properties, maybe some external forces applied to the structure at different joints maybe. And, just as a prototypical example, throughout this lecture, we're going to be referring to this very simple one-dimensional structure, single spring with stiffness K, with a mass or a weight attached to the bottom of the spring, and that weight gives rise to some external force. You can think of this force as being the force applied to the weight of the mass, proportional to the weight or the mass of this kind of block times the gravitational constant of acceleration. All right, let's also make things a little bit more interesting. Obviously, we could go about solving this problem, without any issue, but the key distinction we're going to add to this new problem is we're actually going to make this block be suspended initially above a rigid surface with an initial height h. And this small change is actually going to throw a huge wrench into the works of how we go about solving these basic mechanics problems. So we introduced this kind of additional rigid surface, and you can kind of imagine what's going to happen if we have this weight attached to the spring such that the weight isn't that heavy. What we expect is that the spring is going to elongate by some amount, and it'll be proportional to whatever displaced distance that the block experiences as the spring extends. So under those circumstances, we anticipate there will be some internal stretching in the spring, giving rise to a resultant internal force in the spring proportional to, K times U. And if we have equilibrium, as we usually do, then we can simply state that the equilibrium of all the sum of forces applied to this block has to be, governed by basically the external force acting on this block being equal to whatever internal force is being exerted on the block by the spring. So that's kind of our statement of equilibrium, which gives us K times U equals F external, the classic expression that we've been working with pretty much this whole time. Okay, well, that's all well and good. And you can kind of imagine what would happen if maybe you had a way of tuning this external force so you could increase it. Maybe it started at a value of 0, and then maybe you kind of hung additional weights off of this spring and increased that external force more and more. And you would expect that the slope of this force versus kind of displacement diagram should have roughly a slope of k, or I guess technically this should be 1 over k, but you kind of get the idea. In any case, you increase the amount of displacement as you increase the amount of force up to some critical limit. And clearly, you can see that the limit occurs once the block goes all the way down and comes into contact with the bottom of this rigid surface. So at that point, what happens? Well, once the block comes to rest on this rigid surface, the spring can't extend anymore. The block just has to sit there at this very same location. And effectively what we have is, the displacement of this block really can't be any larger than its initial distance or height above this kind of like rigid surface. So once it gets to this value of displacement, u equals h, then it just sits there, or it rather sits on top of this rigid surface. But that's not all that happens, because clearly you could imagine what's the resulting sum of forces that acts on this block. Certainly there'll be the external force applied from whatever weight we hung on the end of the spring. There'll be still that internal force due to the stretched state of the spring, which will still be proportional to k times u. But there will also be an additional force that arises due to contact between the block and this rigid surface. And this additional force, I'll call R external, is effectively an additional unknown. It's a new variable that we have to solve for such that we satisfy equilibrium. But where our equilibrium equations now have to be modified to include this additional reaction force or a contact force. And this is sort of the interesting scenario where effectively we have two distinct scenarios. One in which the block is not at all in contact with this rigid surface, and another totally distinct condition where the block is coming to rest on this rigid surface and we have to introduce this new variable for this contact force. And if we do this, we also have to respect the fact that we're introducing a constraint on the displacement of the block. When it is in contact with that surface, we insist that the displacement of the block has to be equal to h, its initial height above that surface. So it's kind of like we also introduce an additional equation, u equals h, whenever we have this contact condition come about. So we have additional kind of variable we have to solve for, this reaction force, and an additional equation besides this kind of equilibrium equation. So that's kind of the long and the short of it. Effectively, we have this duality of having two distinct, totally different situations that we have to describe what happens to this block and what are the resulting forces that act on it. All right, so putting all these different conditions together, it's worth noting that in general, we could treat this reaction force as perhaps existing even in the absence of the block, coming into contact with the floor. However, it's worth noting that if, let's say, there is some kind of open distance or kind of some separation between the block and this rigid surface, then we kind of imagine that there really shouldn't be a reaction force here. And under those circumstances, we insist that really the reaction force should just be equal to 0 if, let's say, this open gap between this block and the rigid surface is open. And we can characterize how open is this gap by actually defining a function, which I'll call g, which is in some sense a description of this contact gap, or it is basically a measurement of what's the actual separated distance between the displaced state of this block and this rigid surface, which is really nothing more than the initial height minus the actual current displacement of the block. All right, so this contact gap is also subject to certain constraints. In general, we want this contact gap to be a positive quantity. If it is positive, it means that there is some separation between the block and this rigid surface. But if it closes all the way down to a state of 0 gap, or basically a closed gap, where u equals h, then we expect this gap to be directly equal to 0. And certainly we can't have the block somehow penetrating into the surface. That doesn't make any sense at all. So we do have to constrain this condition such that this gap function is actually subject to an inequality constraint. It's okay for the gap to be open, for the gap function to be greater than 0. It's okay for it to be equal to 0, but it certainly can't be less than 0. So in general, we can describe that condition on what the nature of this contact gap is by asserting that there is this inequality constraint applied to the gap, this so-called non-penetration condition that simply says that the gap can be open, it can be closed, but it can't be negative. So it has to be a function that is greater than or equal to 0. And similarly, for this contact force, this kind of reaction force that arises once the block comes into contact with this surface, we also have to subject it to a few additional constraints on what its value is. If the gap is open, we want this kind of reaction force to be equal to 0. But if somehow the gap were to close, we want this reaction force to, somehow become a positive value. And it only makes sense for this reaction force to be positive if the block actually comes down into contact with the surface. So in other words, if this reaction force has a positive value, it implies that there's some kind of compressive reaction force that's preventing the block from moving further downwards. If, let's say, just hypothetically, what would happen if this reaction force were negative? Well, in that scenario, just kind of using the sign convention for positive being aligned with this kind of particular orientation as I've drawn it here, if it were negative, it would imply that this reaction force is somehow pointing down, which would indicate that this force is applying some kind of tensile resisting force that would resist the block separating from the surface if it were originally in contact and if somehow we removed the weight and the block wanted to move up. And that just can't happen if, let's say, there's no adhesive properties to that kind of interface. If there's really nothing that should hold these two surfaces together, then once we kind of remove that kind of contact constraint from being enforced, then really this force should just go back to 0. So it can only be a compressive force, can't be tensile, or it has to be 0 when the gap is open. And we can describe, again, that constraint on this contact force through this inequality constraint. It has to be a compressive only force. It can be greater than 0, or it can be equal to 0, but it can't be negative. It can't be tensile. And, in addition to our force equilibrium equation, certainly we can work in that additional reaction force just by adding that additional term to our force equilibrium equation. So instead of just Ku equals F external, we also have this reaction force that appears in this term. And if the gap is open, then that reaction force is 0. And we go back to regular Ku equals F external. But if it happens to be in contact with this surface, then we have to satisfy the condition that the reaction force is non-zero. It's some compressive value that prevents this penetration from happening. Now, there's one additional constraint that we have to introduce, and that's this fourth condition, sometimes called the complementarity condition. And this is effectively a statement that says the external force and this gap function, only one of them can be non-zero. And if one of them is non-zero, then the other one has to be equal to 0. That's the only way for this expression to be equal to 0 all the time. So imagine, our external equals 0, then we can have the gap be open. So in other words, the situation where the gap is open implies that the reaction force is equal to 0. And conversely, if the gap is fully closed, if the gap is equal to 0, then this reaction force can be some positive value, indicating that we have a contact condition. So the complementarity condition is really a statement that helps to enforce this condition that really only one of these things can be happening at once. You can't have both of them, which effectively gives us a constrained space for the actual feasible set of solutions that we can have to this contact problem. Either we can have the first case, an open gap, but with 0 reaction force. The contact force has to be equal to 0 in that case, or a closed gap with some non-zero reaction force. The case where contact is, active, I guess you could say. So the complementarity condition effectively means that these two conditions are mutually exclusive. It's not possible to have an open gap and some kind of reaction force at the same time. That would violate this constraint. So that's kind of the main takeaway. And it effectively means that if we were to plot what are the feasible states of the solution on this kind of diagram where I'm measuring the state of the gap function and this kind of reaction force on the same plot, I can be either, along this curve, basically some non-zero positive reaction force, but zero gap, or along this portion of the curve, zero reaction force, but some positive gap. So I can be anywhere on that curve, but certainly nowhere can I be in this open region where they're both non-zero. I can't certainly be on the left end or the bottom end because that would violate, the positivity conditions for both of those variables. Okay, so that's complementarity. And let's see. I want to enforce a few conditions on how exactly we solve these problems in general. So supposing I wanted to go about actually solving this kind of problem as we posed it, how do I use all of those equations that I just proposed? The equilibrium condition is certainly the one that we want to solve most of the time when we're solving mechanics problems. But it turns out that once we introduce this additional variable for this reaction force, it is, in addition to the displacements, a new kind of variable we actually have to solve for and set up a system of equations to solve for it. So if we are going to solve for this extra variable, it's not enough to just solve the equilibrium equations. We need another equation. And that additional equation really comes from one of those two different inequality constraints, either on the reaction force or on the gap function, in order to determine what is this extra variable. What is this reaction force? In the case of an inactive constraint, or in other words, when the gap is open, effectively, I can treat this problem as having no contact interaction at all. And if that's the case, some people refer to this condition as an inactive constraint, where the constraint of interest is the constraint on the displacement of the block. So if I'm not imposing any constraints on this displacement, then I effectively call that the inactive constraint condition. Conversely, if I have contact between the block and this rigid surface, I call that an active constraint condition, where I'm actively enforcing a constraint that the gap has to be directly equal to zero. And that's the equation that I actually have to solve to determine what's the displacement. So under one of these two binary conditions, I need to introduce some additional equation to solve for. In the case of an inactive constraint, the constraint is imposed directly on this reaction force. You have a question?
Yes. So the complementarity statement you said earlier allows the condition where our external equals the gap of when they're both zero.
Let's see. Our external equals zero if, let's say, the gap is open.
So yeah, just need to make this would probably help to make the statement that they're not equal to each other.
That's correct. Yes. They're never necessarily equal, but yes, that's a good point to clarify. Yeah,
the equation allows it, but yeah.
Yeah. The main thing I'll point out here is multiplied together. That's kind of the thing. When you multiply them together, their product always has to be equal to zero, which is kind of the main thing that I'll kind of clarify. Thank you for that. All right. All right. So again, if I have an inactive constraint, or in other words, if the gap is open, effectively, I want this condition. I want that the reaction force has to be equal to zero. So that's my additional equation that I have to introduce and solve for in order to solve for both of these two unknowns, the displacement and this reaction force. So two unknowns, two equations. Okay, so far so good. In the case of an active constraint, I have a different condition. I have that the gap has to be equal to zero, whereas the reaction force could be whatever. We have to determine it basically such that it satisfies equilibrium. All right, but in that situation, the actual additional equation I have to introduce is precisely this gap equation. The gap equals zero, which, if you like, you can rearrange it, and it basically just insists that the displacement of the block has to be equal to that, total initial height. U equals h. So really, there's three different ways that we can go about solving these systems of equations that arise. And I'll kind of briefly go over them. The first way is to actually solve these systems of equations as I've set them up as distinct 2x2 systems of equations with 2 equations and 2 unknowns. So effectively, I get a system of equations that alternately, in the case of an inactive constraint or an active constraint, appears as follows. So the equilibrium equation basically can be rewritten as this first row in this block system of equations. And this additional constraint on the reaction force is this second row, which kind of trivially just has this statement that the external reaction force equals 0. All right. In the second case, we have to replace that second equation. And basically, it looks like just swapping the 1 and the 0 here. And the difference is that we're instead saying that that gap has to be equal to 0. Or in other words, the displacement has to be equal to h. Okay. So slightly different. But the thing I want to point out here is that, again, you get a totally different system of equations that you have to solve depending on whether you have an inactive constraint or an active constraint. So that really serves as the primary challenge to solving these types of general contact problems. You have to kind of switch between the two instantaneously once you go from an open gap and no contact happening to a closed gap and contact is being enforced. So totally different systems of equations. And ahead of time, we don't really know which one is which, whether or not the block will actually come into contact with the surface or not. So in essence, and to kind of summarize the main quandary of contact mechanics, we don't know which one of these will take place. So we kind of have to make an initial guess most of the time, assume whether or not this constraint is active or inactive, then evaluate one of these systems of equations, whichever one we've chosen, and then we have to come after the fact and verify, do we still satisfy our kind of constraints, either on the reaction force needing to be strictly compressive, or on the gap needing to be strictly kind of positive. So those conditions have to be satisfied or checked basically a posteriori. We have to make some initial guess of which one we're going to solve and then try to solve it and then check after the fact. Was that the right assumption? Did we assume the right kind of inactive or active status of the contact condition? All right. So that's the first way that you can do this. Just set up a system of equations, solve it for both of these two unknowns, but the system of equations will involve one of two different extra equations that we have to solve. Now, in the case of a slightly different approach to solving this problem, you can kind of imagine that solving this equation would have been a lot simpler and more direct if I just said, well, reaction force equals 0. So just plug in 0 here, right? It's such a boneheaded move, right? Similarly, if I know displacement, at this point has to be equal to h, just plug in displacement equals h. And then I don't have to solve a 2x2 system of equations. I can just eliminate one of these two variables and then solve for whichever the remaining variable is that I need to determine. So in the case of an inactive constraint, if we make those substitutions, if we say, well, R external equals 0, just plug it in. Okay, we get back to our usual KU equals F external. Just kind of proceed as if there's no contact constraint whatsoever. And then everybody's happy. A lot less work, or at least slightly less work in the case of this 2x2 system. And conversely, if we said, well, U equals H, plug that into this expression, I can rearrange things and then figure out what is the resulting external reaction force just by subtracting over the K times U, which is now K times H, move it over to the right-hand side, and now I have my direct expression for the external reaction force from that contact constraint. So that's another way that you can go about solving this system of equations. Instead, you can just kind of make some direct substitutions and just say, well, either forget about the constraint, pretend like it didn't even exist to begin with, or pretend like you're solving a statics problem. Don't even suppose that the block can move. Just sum up all these forces, assuming that it's fixed in this kind of static location, and then determine, based on just sum of forces, what is this reaction force so that the whole system stays in balance. So very, very kind of simple approach to solving this. And the last way that you can go about solving this is actually more of an approximation. Sometimes it's difficult to solve this problem if you're working with this binary condition where you don't really know, is it in contact? Is it not in contact? Ahead of time, we don't really know. So another alternative to doing this, rather than kind of respecting each of these two conditions, is to actually relax one of the constraints. And the constraint that we relax is the condition that the gap has to be a strictly positive or zero kind of value. And if we do that, then effectively what we're doing is we're saying, well, maybe let's make it such that the block, once it comes into contact with the surface, maybe it can like displace down just a little bit more. Almost like we're not treating this bottom surface as a strictly rigid surface, but such that we have maybe a little bit of elastic behavior in this surface. So once it kind of, the block touches the surface, maybe it can kind of compress a little bit itself. And that's kind of equivalent to saying, let's add an extra spring, but a spring that has, again, this initial separation built into it, but such that once the block does come into contact with that other spring, it can compress. So that's precisely this kind of third approach, which is sometimes more broadly referred to as a penalty method. It's a way of basically saying, don't treat it as a strictly rigid constraint, make it kind of like have some finite stiffness. And in general, if you say, well, make this extra stiffness of this spring really, really high. So just make it super, super stiff, especially in relation to the stiffness of this spring, then we kind of get back to that condition of this being practically a rigid surface. So under those conditions, in the limit, as this artificial kind of contact stiffness, as it's sometimes called, or penalty stiffness, if we make that super high, then we'll get back to the condition of, basically totally preventing, any downward displacement of this, contact spring, if you like. But the nice advantage of doing this is that we can basically generalize this whole statement and almost turn it into a unified statement just by saying that this reaction force should be directly proportional to the amount of compression in this, contact spring. Or in other words, if there is a negative gap indicating that this spring should be put into a state of compression, then and only then there should be some kind of internal reaction force proportional to the amount of compression in that kind of extra spring. If the gap is open, then we assume that the reaction force is zero. And we can express this kind of relationship between the apparent gap between these two objects, between the block and the spring, the penalty spring in particular, by saying that effectively we can say this external reaction force is equal to the penalty stiffness of this contact constraint spring multiplied by this statement that involves these kind of weird angle brackets. And these angle brackets are sometimes called the Macaulay brackets. It's really just a fancy way of saying that if the thing inside of these angle brackets is, let's say, less than zero, then just evaluate this as equal to zero. And if it is greater than zero, then just leave it alone. Treat it as is. So you can imagine if I plug in minus the gap function inside of this angle bracket expression, then if the gap is open, then I'll have minus some positive quantity, indicating that the Macaulay bracket says that this function should just be equal to zero, because the Macaulay bracket of some negative value is just zero. And that's precisely what I get on the left-hand side in the case of an open kind of gap. And on the right-hand side, conversely, if the gap is less than zero, indicating that there's some interpenetration between the block and this kind of surface, then I get minus some negative value, or in other words, Kc times the gap function. So I can plug that value directly into this expression, and now I have some additional term that depends on basically Kc times the gap function. All right, so that's really, really the short and long version of contact in one dimensions. And we could end it there, but I want to provide a few additional insights as to how exactly we go about deriving some of these equations. And it'll be useful, particularly when we come to this subject of how do we generalize this same concept of these contact constraints into the setting of a two-dimensional or three-dimensional finite element analysis. So to understand how we do that, it's useful to actually take a step back to one of the classical principles in mechanics, sometimes called the principle of minimum total potential energy. So in short, the principle of minimum total potential energy says that if I have some mechanical system that has, let's say, some maybe elastic stiffness, and maybe it has some external forces applied to it, then I can quantify what's the total potential energy of this system, of this spring with a mass associated with it, through two separate terms. The total potential energy of the system is proportional to the internal elastic strain energy stored by the spring if it were to be stretched, which you can measure as 1/2 k times u squared. That's the internal total potential energy associated with elastic deformation of this system. And I can also include what's the potential energy of this block. If you like, you can think of this as gravitational potential energy, where if I move the block up, if it has increasing elevation, it has increasing potential energy. If I move it down, it has decreasing potential energy. So gravitational potential energy in this case is really just proportional to F external times the minus of this displacement, assuming this is a positive displacement. If I'd chosen the sign convention in the reverse, then I could have just kind of reversed the sign. But hence why when I define potential energy or gravitational potential energy, I have to include this minus sign. So minus F external times U. All right, so that's the total potential energy of this mass and spring system. And the principle of minimum total potential energy is kind of a magical concept that says that if I can define this total potential energy of this system, then it turns out I can show that for an elastic system, and more specifically, a conservative system, I can find that the state of equilibrium that this system will occupy will correspond to the state where this total potential energy of the system achieves a minimum value. So in other words, this function that I've defined here, this capital pi, expressed as a function of the displacement of the spring, if I choose to minimize this function, which if you like, you can kind of visualize it as being at most a parabolic function of the displacements, which I could plot in this kind of simple diagram. So effectively this parabolic curve. And if I'm saying that equilibrium occurs when the potential energy function achieves a minimum, then that's equivalent to saying, find the kind of minimum point on this diagram, and in particular, find the displacement at which that minimum point occurs. And that will correspond to our equilibrium condition for this system. Another way to describe that condition is to suppose that when I achieve a minimum, I also have to enforce another condition on this function. A minimum occurs when the slope of this function equals 0, right? So in other words, when I reach the bottom of one of these hills, that's exactly when I get my minimum condition, assuming it has positive curvature. Let's see. So if I view that and I say, okay, well, to achieve this minimum, all I have to do is take the derivative of this potential energy function with respect to the displacements, and that setting that equal to 0 gives me my equilibrium condition. And you can kind of see rather magically, we get back exactly what we expected to get. Ku minus F external equals 0. Or in other words, Ku equals F external, the equilibrium equations. And this is sometimes called the variational approach to deriving the equilibrium equations. It's effectively yet another way, apart from the way that we've previously derived, to come up with these equilibrium expressions. Now, all of this applies in the case of a spring and a mass and everything, forgetting about that additional contact constraint. But really, the crucial observation here is that rather than solving some kind of mechanics problem, we've actually converted that problem into an equivalent optimization problem. We're trying to minimize some function which is expressed in terms of this unknown variable for the displacement. And to do that, we have to kind of take its derivative and set that equal to 0. So how does this generalize now if we do include this extra contact constraint? What happens when we include that contact condition? Where now there's a rigid surface, initial separation h, we can measure this contact gap function in the same way that we did before. And effectively, how we change this condition, how we actually go about applying the same principle of minimum total potential energy, all we have to do is say, well, let's still minimize this function, but we have to include an extra constraint. And so far, we haven't said anything about this reaction force. That'll come later. But for now, if all we care about is solving what's this displacement, then we have to introduce this additional equation or an inequality constraint imposed on this displacement. So in the context of mathematical optimization, this particular problem minimized some function of the displacements such that I also satisfy this inequality constraint condition. This is sometimes called an inequality constrained optimization problem. This kind of problem shows up all over the place, from optimization, in a structural context to any kind of optimization problem you can think of. Most optimization problems include these kinds of nasty inequality constraints. So understanding the basic principles of constrained optimization certainly is relevant to understanding and studying contact mechanics, but really it's a very general kind of tool to use and apply in a very broad range of different problems in engineering. So, all right, now that we know that this is what we're solving, we're actually solving an inequality constrained optimization problem. How does that kind of shake out? And how do we apply some of those methods that we previously developed in order to solve this problem now? How do we include this extra constraint? That's the thing we need to work around. And to do that, there's a couple ways that we can do it in the way that we previously discussed. And the first way to do it is by introducing, again, an additional unknown into this problem. Or in other words, take that reaction force that we kind of decided we needed to introduce as an additional variable and properly treat it as an additional variable. But how do we work that into our original system of equations and this principle of minimum potential energy? Well, it turns out it's relatively simple to include this additional constraint. And all you have to do is just go back to your original minimization problem. And instead of minimizing the potential energy, you include an additional term. And in fact, you include this complementarity condition, which I'll remind you, this complementarity condition, basically the product of the external reaction force with the gap function, that always has to be equal to 0 if we're satisfying this kind of binary condition of, either gap is open and there's like no reaction force, or gap is closed and there is a reaction force. So if that's true, if this complementarity condition indicates that this term should just be equal to 0, then it's kind of like we're just saying, take our original total potential energy and add 0 to it. It's kind of funny. It seems like we've done nothing at all, but we've done everything. All right, so that's kind of the magic behind this concept. It introduces this extra variable, this constraint variable, sometimes called a Lagrange multiplier, named after Joseph Louis Lagrange, who came up with this concept in addition to various other contributions to mechanics and which have been formalized in the context of Lagrangian mechanics more broadly. But the idea of these Lagrange multipliers is that they effectively constitute an additional variable that we have to solve for, and which constitutes a variable that is subject to minimization in this new problem that we pose. So we're solving an optimization problem, and we introduce this additional variable such that we include the complementarity condition directly in this optimization objective that we're trying to solve. And all we have to do is just, take that additional variable and multiply it by this original constraint that we wanted to include. If we do that, and then we take the derivative of this potential function with respect to u, then we get back basically all these other things. And it's not just the derivative of the potential function, it's really the derivative of the potential function plus this additional term. So that's kind of a little bit misleading from what's shown here. Technically speaking, this term should be something called the Lagrangian. It's the total potential energy plus the complementarity condition. So if we do that, take the derivative of this whole expression with respect to u, I get the modified equilibrium equation that includes that additional reaction force, that additional unknown we have to solve for. And then the other equation shows up here. Basically, if we take the derivative with respect to the reaction force, we actually recover the gap constraint equation. So that's precisely where we get these two additional equations. And again, in parity with these two unknowns that we have to solve for, which, as we've shown previously, you can solve in a number of different ways, either by setting up this system of equations, solving for the unknowns, u and r external, or doing some other way. Condense out one of these variables and then solve for the other remaining one. And then finally, obviously, if we didn't want to do this Lagrange multiplier approach by introducing this extra variable and increasing the size of the system of equations we have to solve, the other alternative is that penalty-based approach. which is very simplistic in how you would actually go about modifying this term. It really just says, take the total potential energy and add to it some additional potential energy associated with the elastic strain energy of this kind of penalty contact spring. So whatever elastic strain energy is stored in that kind of contact spring, that gets tacked onto this total potential energy. And it's all expressed purely in terms of the displacement variables. And the advantage of this approach is that we don't have to introduce this extra, constraint variable, the Lagrange multiplier for the reaction force. We express everything in terms of the displacements, and it makes this, a lot more straightforward. There's only one equation we have to solve, and only one equation, or rather one, unknown that we have to solve for. So that's really the essence behind this. And you'll see exactly how these concepts generalize to the case of 2D and 3D contact constraints. So understanding these principles is going to be really essential for that. All right. So now that we understand some of the background in the one-dimensional case, we still have a little bit of time. So I'll give you a little bit of the details about how we describe contact between now two elastic bodies. Suppose I had two objects, I'll call them omega A and omega B. And if you go into the classical literature on this subject, you might actually encounter slightly different terminology. Rather than calling these objects A and B, sometimes people refer to these as master and slave. And I put that here really just for reference, but I do want to point out that kind of terminology has fallen out of favor in general. So people have kind of shifted towards using A and B instead of master and slave. Just so you know, because there is a lot of literature out there that uses this classical terminology, and it might be helpful to distinguish how the old terminology maps to the new terminology. In any case, we have these two objects, and on each of these two objects, we also distinguish subsets of the boundary of each one of these objects, which I'll call gamma sub A and gamma sub B. And in general, these two subsets of the boundaries are the potential surfaces of each object that might come into contact. So if you like, you can interpret these as the contact surfaces defined on objects A and B. Okay. So we have to define a few extra things if we want to come up with description of, whether or not these two bodies are coming into contact. And the first thing that we can define is effectively a distance between these two objects. And not just any distance, we have to be particular about specific points defined on either one of these two contact surfaces. So in general, if I have some point A defined on surface A and some point B defined on surface B, I can define the distance between them in the standard Euclidean distance metric. So in other words, take the value of xb minus xa and compute its magnitude of that resulting vector. And that gives me the distance between those 2 points. Now, not just distance do we want to measure, but we also want to measure what is the closest point to any other point given some particular point B on surface B. So imagine I said, okay, let's look at surface B and just choose this particular point xB. Now, given this point, assuming it's fixed, what is the closest point to point B on the opposing surface A? And to determine that, we can define that closest point, that's closest projected location of point B onto surface A as exactly this XA with a bar over it. That's the so-called closest point projection of point B onto surface A. And it satisfies this condition that X bar sub A is actually the position which minimizes this distance between XB and any possible point that might lie on surface A. So in other words, just pick the point X bar sub A that is closest to XB. And that's kind of our closest point projection. Okay. Now it's interesting to note that if I actually go about defining this closest point projection, this X bar sub A, I also note that assuming these two surfaces are relatively smooth, it turns out that I could define what is effectively the derivative of this distance function evaluated at this particular pair of point locations, xb and its closest point projection. And if I take the partial derivative of the resulting distance function with respect to this point, I actually get a normalized measure of this unit vector, which happens to lie basically strictly normal to this surface of, basically contact surface A. So if I like, I could go about defining this normal vector in any number of ways, but it is effectively this vector that is strictly perpendicular to this surface at this kind of projected point location. So I have now a normal vector that points basically from point A to point B and which has unit magnitude. And then lastly, we can define a gap function, the thing that actually measures the separation between these 2 points, but which measures that separation in a way that measures distance with an additional sign attached to it. And that's essential for determining whether or not something is penetrating in contact or with, an open separation between these 2 points. So the resulting gap between these 2 points, x bar sub A and xb, is determined through this gap function, which in the case of, two-body contact can be evaluated as basically this particular vector dot product with this normal vector. So you can kind of imagine that if this normal vector always has an orientation that's outward with respect to this particular body, then if this distance vector is open, then the gap function will be positive, and I'll have this open gap condition. No contact will be occurring. Conversely, if this point were to somehow penetrate into this body, under those conditions, the orientation of this normal will still be outward with respect to this body, but the distance vector between these 2 points will be kind of pointed in the opposite direction, such that the resulting gap function will be negative, indicating that I should have enforced my contact constraint because effectively those 2 points are penetrating into one another. And the way that I enforce that interpenetration constraint is by introducing an extra variable. And it turns out that extra variable has the interpretation as being a surface pressure or a contact pressure that acts per unit of surface area on this original surface A. So we've defined in parity all these new terms. We have a gap function that just measures the closest point between, 2 adjacent points on 2 distinct bodies. That gap will be kind of open if the gap function is positive, and it'll indicate that there's interpenetration if the gap function is negative. And to get rid of that interpenetration, we have to introduce some new contact force, or in this case, a contact pressure that pushes the 2 objects apart if they were to otherwise come into contact. So in parity with all of the things that we previously developed, we can come up with this non-penetration condition that says that the gap function always has to be greater than or equal to 0. We can introduce in parity also a compression-only description of that contact pressure. It can only resist force and push the bodies apart if they come into contact, but it can't hold them together. It can't be tensile. So the contact pressure has to be a strictly positive or possibly 0 value. And then finally, we have the complementarity condition. The product of the contact pressure and this gap has to always be equal to 0, indicating that only one can be non-zero, but in order for one to be non-zero, the other has to be equal to 0. So that's kind of the long and short of how we're going to set up these 2-dimensional contact problems, but unfortunately, we've run out of time. So I appreciate your patience, and we'll pick up where we left off on Wednesday. All right, I'll see you then.